Let's go into the tool now and show you how to enter all the data that you need in order to make this a success. On the left-hand side here, you'll see the exact same model that we were just looking at. I should state that there are plenty of different types of materials that you can use to build these. We currently have HDPE culvert in there. However, I would suggest that whatever you can get most cost effectively is probably what you should use. Now that you're at the tool, you'll notice that the first cell has been pre-filled out for us, and it is the volume of the greenhouse. The reason we have a volume up here is because we're going to be designing this subterranean heating and cooling system to manage a certain number of air changes per hour. The next cell you're going to enter is the number of air changes per hour that you expect to push through this system. The rules of thumb that I have found over the website and with other systems that we have directly and other systems that we've directly and indirectly worked with have been between 4 and 10 air changes per hour. I recommend starting at 4 air changes per hour and trying different airflows with different system orientations. 4 air changes per hour in this particular greenhouse is going to mean a fan that's operating at 533 CFM. The next thing that you're going to determine is how many pipes per lift you're going to install on this system. So in this picture we have 3. 1, 2, 3. However, you could very easily just do 2, or you could try doing 1 as well. We'll keep it for 3 right now, and then we'll experiment with a different number later. Horizontal distance between the heat pipes is going to be the distance between lifts. So this bundle is a lift, and it's the distance between this pipe and the next pipe right here. And so this distance is going to determine how many pipes fits into the total length of the manifold. So we're going to also keep this at 3 feet right now. As we're using a culvert pipe, the interior surface of that pipe we're going to assume is rough, which is going to change the flow regime within that actual system. I should mention that it's not necessarily important for the pipes to be rough themselves. It can be just as effective with a smooth pipe as it is with a rough pipe. However, it will change the type of fan system that you'll end up using. I'm going to assume that we're going to use 4.5 inch diameter weeping tile as our primary heat pipes moving between the two manifolds. In the next cell, the sheet asks you to determine how wide these manifolds are. This width is going to be dictated by the shape and size of your greenhouse. So for this particular greenhouse, we're going to use 20 feet. As a result of this information, the calculator is telling me that each of the heat pipes is going to convey 27 CFM, and the calculator itself has done a quick check to make sure that we have not exceeded the airflow for that particular pipe. And so it's giving me a green light and saying that I'm okay. It's also telling me that the recommended inlet and outlet duct size is 12 inches. So this has now specified the size of these primary manifolds for me. And as a result of the calculation, in order to stack the chances of success in my favor, it has given me a low and high CFM rating for the fan. So when I go and purchase my fan, I will try and find a variable speed fan that can operate between 400 and 1000 CFM. Let's do one more example and show how the tool can be placed out of range so that you understand where the limitations actually are. So using the same greenhouse example, I'm going to change the number of air changes to 8. I'm going to keep the same number of pipes per lift and the same distance between the lifts, the same roughness, the same diameter, and the same length. And you'll notice that my airflow in the individual heat pipes has gone up to 53, which exceeds the 50 CFM over here. So as a result of that, we're trying to push too much air through each individual pipe, and the system is going to stall. The solution to this is either to increase the diameter of the heat pipe. So we can try increasing to a 6-inch pipe. However, you'll notice that the airflow rate is not high enough for the 6-inch pipe. So now the error message that I'm getting is that I do not have enough airflow moving through that pipe to be successful. So I'm going to move back down to the 4.5 inch pipe. And then in order to get more pipes into the system to reduce the airflow, in other words, the air is being spread out amongst more pipes, I'm going to change the distance between the pipes to 2 feet. As a result, I ended up increasing the number of tubes in the system, which reduced the total CFM per pipe and gave me a green OK, meaning that my airflow rate is within range. Let's try one more example and see if we can make this fail, just so you get a sense of how the tool actually functions. Let's try 5 air changes per hour. We're going to try a distance of 4 feet between lifts, and already we've hit that low mark. So now what the tool is telling us is that we don't have enough airflow through these pipes, and so we have to increase the amount of airflow. So we can either increase the distance between the pipes to reduce the total number of tubes. We can't really go below 4.5 inches in diameter to increase the airflow. Or we could decrease the manifold size, so there's a smaller system in the actual greenhouse itself. So as a result of making a smaller system, again, we have increased our airflow within range, and the system is giving us a green light. Now, it should be noted that you don't necessarily want to have a small system. In an ideal world, our subterranean heating and cooling system is going to be as large as possible, consuming as much of the volume inside of the greenhouse as possible to distribute as much of the heat throughout the entire space as we can. If you're looking to design your own passive solar greenhouse and want help in choosing R value for your walls, a glazing material, the amount of heat or size of heater required to heat the greenhouse, your lighting system, thermal mass calculation, as well as designing a subterranean heating and cooling system, you will find that this tool makes passive solar greenhouse design infinitely easier. These videos will show you how to use the tool, and if you're interested in purchasing the tool for your own passive solar greenhouse design, you can find information on how to purchase the tool at Small Farm Academy in the link below.